Okay, so hello everyone. My name is Victor Jung, and I'm going to talk about MDDs and more specifically about operation between MDDs. So I'm a bit upset because I'm the first one talking about decision diagrams, so I have to keep some notions to help the presentation be more comprehensible. So I hope it will be fast. So first, decision diagram is simply a rooted directed acyclic graph. So figure on the right. So it does not contain cycle and arcs of directions. So the consequence is that you can represent a decision diagram layer by layer. Okay. So more specifically, MDD is used to represent some multivalued functions. And in my case, what I do is I use MDDs to represent constraints. So here we have the MDD of all different constraints, where we have the domains of all variables set to A, B, C. Each layer represents a variable. So the first layer is assigned to the X1. The second layer is assigned to X2, and last layer is assigned to X3. Each arc represents an affectation. So the first arc from root to the node to the left means that X1 is assigned to the value A. And each path going from the root to the terminal node, which is called TT, is a valid solution of the constraints. So now I'm going to talk about important operation, which is the intersection. So it is important because when you solve a CP problem, what you do is you do a conjunction of different constraints. And if you use MDD to represent your constraints, then doing a conjunction of constraints is equal to making an intersection between the MDDs. So this operation is quite expensive because at most, what you do is a Cartesian product of the number of the nodes you have. And knowing that MDDs can be very, very large, it can be very, very expensive and have exponential behavior. Okay, so I will give an example to show you how an intersection is performed. So I want to perform the intersection between these two MDDs. So the one on the left is just some random values, and the one on the right is the all difference. So what we do is we first create a root, which will be linked to the two roots of the two MDDs, so A0. Okay. Yeah. And what we do is we ask one of the two roots what are the arcs. So let's say we ask 0, what are the arcs you have? So 0 say, I have an arc 1 going to the node 1. And we ask A if he has the same arc. And he say, yes, I have 1 going to B. So we create B1 going, having an arc with label 1. And so we repeat this process up until we reach the terminal node. So here we can see that the node E5 doesn't have a children or a child because 5 only have arcs with label 1 and E only has arc with label 3. So they don't share any arc, so you don't continue the path. At the end, you remove what is useless and you have the solution of the intersection. Okay. So why am I talking about this? So my motivation is that when you are intersecting multiple MDDs, it may be possible that the final result fits in the memory, but somewhere beyond, between the process, multiple process, it can happen that the memory explodes. Like, So either one of the base MDD you want to intersect with cannot simply fit in the memory, or the intermediate MDDs. So let's say that you want to do a 5 intersection, you will do 1, then another 1, etc. And that's what I call intermediate MDDs. It's the intermediate results of the intersection. And a simple example is that when you have no solution of your problem, the MDD is empty. So obviously it fits in memory, but you cannot know in advance if it will be empty or not. So the goal is to approach as much as possible the idea that if the result fits, I want to be able to compute it. Of course, it's very complicated, but okay, it's the goal. So I will present first the method to do on-the-fly intersections. So let's go. The principle is simple, is that we try to inject the construction process inside the intersection process. And the consequence of that is that you have to provide a definition of the MDD you want to build. So that's not really a drawback, because when you are building an MDD, generally you do it by defining a general rule and not with an ad hoc definition. So no problem for this. So the architecture. So instead of asking the two MDDs if they share a common arc, we simply ask if the transition is valid for a certain constraints. So we ask, is the transition valid? No, then we don't do anything. And if yes, we try to see if a node is already existing, corresponding to the state we are building. And if yes, we give the node, and if no, we create it, then we give the node. So an example, so the same example as before. I want to intersect this with all different constraints. So what I do is I first create a root. I iterate over the arc of the first root, and I say, is this valid? So yes, it is valid. So I build the all difference at the same time as I do the intersection. And doing so, I will not compute the whole MDD, which will be quite useful, as I will show you later. So when you give a definition of when you give a definition of the different states, what you can do is you can try to compute how many nodes you are going to create according to the rule you defined. So this will allow you to know if your MDD can fit in memory or not. So for instance, for the all different constraints, the state is simply the set of the values that were taken, and the various function I presented earlier. So a state is valid if obviously the value is not already in the state, and the next state is simply adding the value we are taking to the set. So with this definition, we can know how many nodes will have our final MDDs. So simply said, generally in all different constraints, what you have is n, which is equal to v. So, and you have 2 power n nodes in your MDD. So it's exponential. I will show you a proof later. So we will consider n to be equal to v in the proof. So, and for the sum, the state is simply the current value of the sum. The next state is simply the addition of the current sum and the label, and the transition is valid if you can reach the bound depending on where we are. So it's pretty simple, but I don't know if I make it clear. So the number of states for the sum is this. But it's not really important. what is important is that this bound is achieved when the values in these are arranged, so they are continuous. And the second remark is that this value can also be bounded by the upper and lower bound of the sum. So what I mean by that is that at some point you can see that your sum, you cannot reach either the upper bound or the lower bound. And in that case, you know that this state cannot exist. And of course, it will be removed during the building process. So this process of doing the computation as you go can be quite efficient and have exponential gain. And I will show you a proof of that. So for that, I will create a special MDD. So first generate a branch like this. So x1 is a set of values. So here I took the set to be equal to 3 and x equal to 3 for my example. I duplicate the branches to form this MDD, and then I duplicate this MDD and concatenate them like this. Okay. So let's try to do the intersection with all different constraints. So what I said is the number of nodes in all different is 2 power n. Okay, so each branch, so I call this a branch. When you intersect it with all different MDD is 2 power the number of the values that are in there. Okay. Okay. Oh, sorry. So what I do is I replace each branch with a single arc that I call meta arc, and still the same. So it's still exactly the same MDD. Okay. And when I do the intersection between this meta MDD and all different MDD is meta and all difference, I guess. So it will give something like this, where each arc is an all different MDD with 2 power x1 nodes. So the total number of arcs in our meta MDD is x times 2 power x minus 1. So the number of arcs. And by combining the first remark and the second one, we can compute the number of nodes in our total MDD, which is x times 2 power x1 plus x minus 1. Okay. So that is what we obtain when doing the intersection on the fly. And by the classical approach, I will have to build the all difference for x times x variables. So that will give 2 power x minus 1 power x, power x1 power x. And the difference between the two is exponential. So here we go for the results. So I will first present the results of the theoretical example I show you. So I tried to build the all difference with n equal 25, and I had a memory out for n equal 24, and so performing the intersection seems impossible if you want to try with higher values. And when trying the approach of building on the fly, so here the first one is for n equal 25. And it's the intersection. So we can go up to 100 pretty easily. So it validates the results of the exponential gain we show. And we can obtain same result for a lot of problem here, the core sequencing. Which is interesting is that when doing the on-the-fly intersection, we go up to 100, so we close the problem, while the other method doesn't work. Oh yes, I found this interesting, is that MDDs are naturally sensitive to the order of everything, the variables, the intersection, but this on-the-fly method exacerbates this sensitivity. So, for instance, when doing the core sequencing, just changing the order of the constraints I apply, I have a factor 10, and when changing the order of the relaxation, it's even more. I don't know what to say, but when first doing the first option, then the second one, then the third one, we have output, no solution. But when doing the first one, the second one, and the fourth, I have a memory out. So it doesn't even mean that it will output no solution. If it outputs something, I just can go further on the intersection. And finally, it's the problem on the constraint, on building a constraint. So this process, I will not detail this process because it will be a presentation tomorrow, the subject of a presentation tomorrow. But what is interesting is that we can apply this this process to first compute MDD with small precision and use it as a canvas to improve the precision as you go. And what we obtain is like factor up to 100. So pretty nice. And to conclude, so just this method has better memory usage, faster execution time, and simply better than the classical intersection approach. However, it does not change the exponential behavior of the intersection. And doing multiple constraints intersection at once is generally not worth it. It's worth it in very niche cases, but generally not. Okay, so thank you for your attention.
You have a few minutes to take a few questions. Yes.
Very interesting. Do you have insights on the inverse operation when I take an MDD based on your study? I want an MDD that I know is going to be exponentially large, but I can break it to smaller MDDs that the intersection is the resulting one.
Okay.
Do you have any insights from your work that you can get the inverse operation?
The inverse?
Yeah.
What do you mean by
inverse?
inverse?
Is taking the MDD and break it in a way that the intersection is the full MDD. That would be very interesting format.
I really don't know the answer of your question. So I'm sorry.
Yes. Just a remark. You know the results of knowledge compilation?
For?
Knowledge compilation, AC.
No, I don't know.
Okay. That's too difficult to explain. But you know, they look at point time operation, representation, succinctness in the representation. You probably should think.
Okay. Yes.
Is it interesting to do it as a binary tree, the intersections like pairwise and group?
Binary tree?
Yes, if you have a binary tree, you do the intersection pairwise, and then you do one level up, intersection up to the root. To keep them small.
Yeah, instead of doing it in sequence, you do instead of pairwise and then you go up.
It could be interesting. However, how I understand it, I think it should not reduce that much the size of the whole MDD you obtain. Because MDD are very counterintuitive when you try to think about the intersection and the size. So it's very difficult to answer this. It could be interesting. Okay, that's for sure. We should try something like this, but I don't know if it is good or not. But it is interesting, yes.
Okay, I think it's time to maybe very, very quick question.
Can you create your intersection graph? It looks like you are doing EFS, but we could EFS or that first search. Would it improve somehow the memory footprint?
Okay. So when you are trying to do DFS on MDDs, generally MDDs are representing a very large number of solutions. And when you are doing DFS, what you do is you extract every solution one by one because you are doing a DFS. And so for the information, some of the MDDs I worked with had like 10 power 30 solution in it. So DFS is very complicated in that case because you have to extract literally 10 power 30 solution one by one. So it might be interesting in some cases where MDDs are not very, how can I say, compressed, when they are very large and the path all looks like straight, they are not converging in any way, in any sense. So here it is interesting to do DFS. I know some problem with it. It is interesting, but generally it is better to do in BFS.
Thank you.